In this video, we're going to look at logic, and we're going to look at an intro to logic in general and quantified statements. This section within the book discusses the history of logic, and it goes into how the ancient Greeks were attributed with the way that we analyze the way humans think and arrive at conclusions. Aristotle is the Greek philosopher that is known as the father of logic. However, in mathematics, we attribute symbolic logic to George Boole. We've already discussed a little bit of logic concepts when we looked at set theory, and we talked about intersections versus unions, and we talked about and versus or, how in order for it to be counted in an and statement, both things needed to contain that object, and that was for intersections, whereas for or, if one set or the other had it, it would count. We saw that, and then also when we looked at probability, we talked about and statements and or statements, and that ties back into what we'll see when we're looking at logic. So this I'm very excited to go over with y'all. Please make sure that you watch the videos, and if you have any questions, you reach out and let me know. The first thing we're going to look at is we're going to look at the meaning of statements, and we're going to look at negations. So a statement is any sentence that can be judged as either true or false. We can label a statement as being either true or false, and we call that assigning a truth value. So we might discuss the truth value of certain statements. We're going to look at statements or these examples below and determine if it's a statement or not. So the first one, eat your breakfast, that is a command. It doesn't have a truth value. So this would not be considered a statement in terms of logic. Texas is a state in the United States. That is a statement because it's either true or false. Texas is either a state or Texas is either not a state. So this is a statement. Is this the best of all possible worlds? Well, that is a question. It doesn't have a truth value, and it's also, if you were to answer that, it would be your opinion, right? So this is not a statement. And I'm not answering that question. I'm not saying, no, this is not the best of all possible worlds. I'm saying, no, this is not a statement. Then we have Justified is the best show of all time. First off, I've never seen the show Justified, so I don't know if that's true. But this doesn't have a set truth value because it's based on an opinion. So this is not considered a statement. And then the last one, the current president is an independent. That has a definitive truth value. It's either yes or no. It is true that he is an independent, or it's false that he is an independent. So this is an example of a statement. And we can assign the truth values. Is Texas a state in the United States? Right now, we can say that is true. Okay, the current president is an independent. We would say that that is false. We can assign those truth values. For the other ones, they're not considered statements. We can't assign truth values. One of the concepts we're going to look at is negation. And that happens, we use negation when we want to change the statement to its opposite meaning. Oftentimes we think of this as changing it to the opposite or to the not. So if you said today is Saturday, the negation of that would be today is not Saturday. And it also changes the truth value. So if I said today is Saturday and it is Saturday, then that statement is true. If I said on a Saturday, today is not Saturday, that statement would be false. It would change that truth value. So now we're going to jump into looking at this in terms of symbolic logic. And the reason why we call it symbolic logic is we use letters to represent statements. And because we do that, we often make generalizations about the way these sentences work and produce different truth values. Okay, so when are certain statements or compound statements true? Another thing I want to point out is that in our examples above, those were all considered, the B example and the E example that were statements, we consider those to be simple statements because they only contain one part. If they had combined multiple statements or ideas together, we would think of them as being compound. So an example of a compound statement would be if I were to say, In the United States, you must be 18 years old to vote, and the legal drinking age is 21 years old. That's a combination of two ideas combined together with an and, which is an example of a compound statement. Okay, so let's go back to looking at these negations. So we're looking at changing statements to its opposite meaning, changing to not, it changes the truth value. We're going to let these symbols, P, Q, R, and S, represent the following statements. Well, we only need two of them because there's only two statements, but we have the first statement is P, and that represents the statement one plays hard. And the statement R, which stands for the commute to work is not long. So to negate the first statement, P, one plays hard, you might say one does not play hard. In the second example, we're negating the statement, the commute to work is not long. So if you think about it, you could think about this as being a double negation, because if I were to say the commute to work is not long, that's the same thing as saying that the commute to work is long. Now, something to know about our book and the way we address things is that the book would treat this statement up here that I'm putting an arrow next to, because it's the not statement, they would actually treat that as the not R, and they would treat this one as the R. Okay, so just keep that in mind. Make sure you read the context and see what it's asking you to do. If it gives you a not statement, you can write that as a negated statement. So if I were to say this statement, Anna drives a Ford, and that's my statement, and let's call that P. Not P would be Anna does not drive a Ford. Okay. So if this statement is true, it is true, I drive a Ford Fusion Energy. Okay. So if this statement is assigned the truth value of true, then this statement is assigned the truth value of false. Let's change this for a moment. Let's think about my sister, who y'all don't know, but she's really nice, and her name is Amy. And let's say I replace my name with Amy drives a Ford is my statement P, and Amy does not drive a Ford, which is my statement not P. And my sister drives a Honda. So let's say that makes this statement false. And if this statement is false, then when you say Amy does not drive a Ford, well, that is true. So the negation changes the truth value that's assigned to the statement. So next we're going to look at quantified statements. And a quantified statement is a statement that contains all, some, or none. We have to be really careful when we negate statements that contain these words, because you have to think about what makes these statements true and what would provide like a counterexample and prove one of these statements false. Notice this little note. We have some does not necessarily indicate more than one, but it is equivalent to at least one. So that means if one person made this statement true, then it would be true. So we're going to look at these kind of in terms of these diagrams, which are called Euler diagrams. We could also think of them almost as Venn diagrams. We're going to label which one is which. So we're trying to figure out which one of these diagrams here goes with which one of these statements here. So let's start with some A are not B. So some A are not B. That means that there's elements in A that aren't in B. Well, that would imply elements in A that at least one element in A that are not in B, which implies this diagram right here. We have this shaded region in A that is not part of B. We could also represent that with this? If that one's B and this one's A, we have some elements in A that are not in B. So this one could be represented by one of those two diagrams. That's different from the second one, all A are B. That means that everything in A is also in B. And that's just this example here. Everything in A is contained within B. We have some A are B, which means at least one of the elements of A are also in B, which would be this one. Lastly, we have no A or B. So that means nothing in A is also in B. That's when we have these two disjoint, not connected sets or circles. Okay, so think about what it means for all to be part of something, for none to be part of something, and for some to be part of something. So I'm going to draw a Euler diagram or Venn diagram to represent each of these quantified statements. So all men like football. So this outer circle is going to be people who like football, and the blue circle is going to be men. So black circle is football. Like football. Okay. So then we're going to have, for some men like football, we have the people who like football in black, and some of the blue, which represents the men in this case, overlap with liking football. If I were to say no men like football, those two circles would be disjoint. These are the people who like football, and these are our men, and there's no overlap. Okay? And then some men do not like football, and we can represent that two ways. We could represent it with, we have football, and then we have the men. However, that might not be a good representation of this situation because you might have women who like football as well. So that might not be an excellent representation. So in this case, we'd probably want to draw it as some men like football and some men do not. Looking at those previous statements, we want to think about what's the bare minimum that you would have to show to disprove each statement. So if you were to say all men like football, what would you have to do to show that that's not true? Well, you would just have to find at least one man who does not like football. Okay? If you had the statement no men like football, in order to disprove that statement, all you'd have to find is at least one man who does. To negate or disprove that some men like football, you'd have to show that no men like football. And to disprove that some people or some men do not like football, you'd have to prove that all the men like football in the world. Good luck with that. My husband does not like football. All right, all the men like football. Negation of all of something is that some are not. And the negation of some are is that none. So not one of A are B. None of A are B. So these are negations of one another. Each of these negates the one that the arrow is pointing at. So thinking about that, in terms of these statements, let's negate some statements. Let's just do 3 of them. Some people like football. That's what everyone else calls it in the world. Some people like soccer. Well, to have the negation of that, you would say nobody or no one likes soccer. Okay? To negate are, which is nobody is asleep, then you would say some people or somebody is awake. Sorry, somebody is asleep. You don't want to negate or change more than one thing. So this has to be consistent. My turn of phrase was incorrect, but the concept is if nobody is asleep, to negate that, somebody is asleep. And then for not Q, it says all athletes are musicians. So the negation of all are is that some are not. So this would be some athletes are not musicians. So with logic, I'm going to kind of start this off by saying, like, I understand this might be a little bit different in your way of thinking, but I think that it's imperative that we have the ability to critically think about the truth of statements. And I think that given the world that we live in and the information that's presented to us, it is extra important that we have the capability to think about what makes a statement true. Okay, so, and really thinking almost about like life and philosophically speaking, this is a super important skill. So this wraps up our part 1 for chapter 3, section 1. We'll get into part 2 in the next video.